Hi, my name is Tom Hoeffel, and this channel is all about helping students learn chemistry. In today's video, we're going to be talking about lattice energy. In the previous video on ionic bonding, we talked about how metals transfer their electrons over to the nonmetal, in this case, sodium transferring its electron over to chlorine. And in this video, we're going to talk about why that happens using an energy diagram. And then we're also going to explain this idea of what lattice energy is. So let's get right into it. Okay, so on an energy diagram, before this bonding ever occurred, we had sodium atoms and chlorine atoms. We're going to put it kind of at this level. And the first part of ionic bonding is the electron's actually going to be removed from the sodium. Now, there's a vocabulary word that we give for that, okay? Ionization energy is the amount of energy required to remove an electron. And what we're going to do is we're going to remove that electron from the sodium. Now, that's going to cost us energy. So in this energy profile, the energy is going to go up due to taking the electron off of the sodium. Now, when we take the electron off of the sodium, it's going to create a positive ion. Okay, so when the electron is removed, it creates a positive ion of sodium. So we're going to end up with a sodium ion. We're also going to have an electron, and then we're going to have the neutral chlorine. Now that costs us a certain amount of energy. And the amount of energy that it cost us, I'm going to look up the ionization energy in the book, and it says it's going to cost us 496 kilojoules. So I'm going to do ionization energy, and the cost was 496 kilojoules. Now, I hope I get a return on my investment, because there's this theme in chemistry: as the more energy you get, the more instability you have. Okay, the lower the energy, the more stable something tends to be. Okay, so what we're going to do, we've taken this electron off of the sodium, we got the sodium ion, and then we're going to put the electron on the chlorine. Take the electron, and we're going to put it on the chlorine. Now, there's another definition called electron affinity, and that's the amount of energy released when an electron is added to an element. So what we're going to do is we're going to add that electron to the chlorine. I'm going to get my book out, and I'm going to look up the value for the electron affinity, and the electron affinity for chlorine is 349 kilojoules of energy released. So that's going to be a negative 349. Now, that doesn't return us to where we started, because it took us 496 to pull the electron off, and we're only returning 349. So maybe somewhere right around here, and I'm going to label this electron affinity. And electron affinity was 349 kilojoules according to my textbook. Now, what that leaves us is with the electron now on the chlorine. So what I have right now is a sodium ion that's positive because we tore the electron off. And then we have a chloride ion because we put the electron on the chlorine. And when I look at this, it really doesn't make a lot of sense as to why this would ever occur. Because if we have to invest 496 kilojoules to remove the electron, and we'll only get 349 kilojoules return on our investment, that doesn't seem like a good return, because I don't think I'd be willing to give up $496 to get $349 back. Seems like a bad investment. On an energy profile, it also looks like these ions are unstable relative to the neutral, elements, because the neutral elements are actually lower in energy, a little bit more stable. Okay, so why in the heck would this ever happen? Okay, now I do know that it happens because I know what sodium chloride is, and maybe you do too. Okay, sodium chloride is the salt that we put on our French fries or we season our mashed potatoes with. Okay, and last time I checked, when I leave my salt shaker out, when I come back the next day, there's still salt in my salt shaker. It's not decomposing back into just sodium atoms and chlorine atoms. Okay, it's staying as sodium chloride. So there must be something else involved here. Okay, and it all comes back to lattice energy. Okay, so The answer to this whole dilemma here is that the sodium ion and the chloride ion, they don't stay separate. They actually bond together to form this lattice structure. Okay, so this is actually a lattice of sodium chloride. And as we investigate a little bit, just to let you know, the black spheres right here, those are the sodium ions because cations are significantly smaller than their parent atom. And then the light blue ones are going to be the chloride ions because negative ions are significantly bigger than their parent atom. So the light blue is the chloride, and then the black ones are going to be the sodium. And if we take a look, at this sodium, okay, it's actually bonding to 6 chlorines, one to the left, one to the right, one on top, one below, one coming out towards you, and then one back here in the back, okay? So when sodium and chlorine bond, it's actually kind of like a 6-to-6 ratio because the same things happen with the chlorine. Left, right, top, bottom, coming at you and coming, towards you, okay? And so it's actually a 6-to-6 ratio, but the part that we're really only looking at is just one portion of the lattice structure. We're just actually only drawing a Lewis model of these two. But when it actually bonds, when the sodium and chlorine actually bond, it creates this three-dimensional lattice structure. And through the formation of those bonds, lots of energy is released. Okay, so we're going to release some more energy when the sodium and chloride ions come together to form all of those ionic bonds. So we're going to put in here the formation of bonds to make a lattice. That's Lattice. It's not lettuce, it's lattice. Okay, so I'm going to look up that value for sodium chloride. I have it over here on the side. It's 788 kilojoules of energy is going to be released through this formation of bonds to make that three-dimensional lattice structure. Okay, so if you asked me, would I invest $496 to get back 349 plus another 788 in return energy or dollars? The answer is yes. I do that all the time. I would do that every day and twice on Sunday. That's a great deal, okay? And you find out that this compound, sodium chloride, is going to be much more stable than the sodium atom and the chlorine atom altogether. But it's because we formed all of these bonds. Now, one of the misconceptions that people have coming into chemistry is they actually think that energy is released when you break the bonds, and that's not true, okay? If I want to come in here and break all of these bonds, it requires energy for me to do that. It's actually the formation of bonds that actually releases the energy, and that's why I have negative numbers here, is because it's actually releasing energy. So it requires energy to remove an electron. Energy is released when an electron is added to the chlorine, and then the formation of all these bonds releases some more energy, and that's what makes this sodium chloride so stable, is through the formation of all of these bonds. Now, when we talk about lattice energy, the definition is actually kind of the reverse of what we're talking about right here. It's not about the formation of the bonds. The term lattice energy, if we had a definition for it, it's the amount of energy required to break all of these bonds. And if we did that, there'd just be a whole bunch of ions laying around. So lattice energy is actually taking the compound and separating it into its individual ions. And that would require energy. And that's why the number over here is positive 788. Okay. But if we form the bonds, that's going to release the energy. So once again, energy will be a positive number when energy is required to break all the bonds, but the energy will be negative if these bonds are being formed as they are going from here to here in our energy diagram. So the last piece that we need to talk about is the strength of these lattice. Okay, so a lattice can get really strong if these bonds get really strong. Okay, and then it would require more energy, hiya, 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 to break them up. Okay, so what makes a lattice really strong? Well, let's investigate the table that we have over here. Okay, if you look, here are some values for different lattices. For example, the sodium fluoride is 910, and as we go down, we can see that the lattice energy is actually decreasing. So it's easier to separate sodium iodide. It only requires 682, where to separate a whole bunch of sodium fluoride would cost us 910. So the lattice of the sodium fluoride is a lot stronger than the sodium iodide. Now, why is that? Okay. Well, the sodium is constant. The only thing that's changing is the halogen. Okay. And what you'll find out is that the iodine is much larger than a fluorine. Okay, so if these ions are able to get closer to each other because of them being small, that increases the lattice energy. And the reverse is true. As these things get really big, it'll be easier to separate them. So what we call bonding distance and lattice energy is going to be inversely related. Okay, so this is my lattice energy. I'm going to put bonding distance as a denominator. Okay, so bonding distance is going to be the denominator. As the distance, bonding distance increases, lattice energy decreases. And I'm going to show you a couple examples of this. Let's say I have two small atoms. This would be the bonding distance. It would be really small. Okay. If you get these things close to each other, there's a lot of attraction. And if there's a lot of attraction, it's going to be harder to separate them. Versus then what happens if we have one small one and one big one. Okay. Well, this bonding distance is larger than this bonding distance. And what's the biggest one is what happens if we have two things that are really big. This bonding distance from here to here would be larger than this one, and this one's larger than this one. So as the bonding distance increases, that will decrease the lattice energy. As the bonding distance or the atom gets bigger, because as we go down the periodic table, atoms get bigger, okay, the lattice energy is decreasing because we're getting a larger and larger D as we go down the periodic table, okay? So that's going to be one factor, is what we call bonding distance. You might see this equation sometimes as r squared, which would be the radius of this atom and the radius of this atom. I like to just use d, which is the distance from one nuclei to the other of the elements that are actually bonding together, okay? There is actually another factor here, and we're going to take a look at our things up here. I have kind of like dividing lines here and here, which shows some significant changes in lattice energy. If we look up here, the lattice energy is somewhere between 680 and 910. And then when we jump in this category, it jumps up to 3,795. And then down in this category, 7,547, which is a huge number, okay? It might be hard to see, but everything in this column deals with a +1 and -1 ion, okay? This is a +1 and -1, this is a +1 and -1, and so is a sodium iodide, okay? When we get to magnesium oxide, though, the charges change, okay? They change to +2 and -2, and you get this big jump in lattice energy, okay? And then down here, it's a +3 and -3. And once again, you get this big jump in lattice energy. So if we take a look at our lattice, okay, as the charges of the ions become larger and larger, they're attracted to each other more and more. And as long as the more attraction you have, the harder it's going to be to break up the lattice. Okay, so a +3 and a -3 is going to be much stronger than a +1 and -1. So the two factors that we have is going to be charges and then how close that we can get to them. Think of like having, magnets. As you get close, get them close, okay, there's a lot of attraction, okay, and then it requires more energy to separate them. And that's what lattice energy is, the amount of energy required to break all the bonds and create individual ions. Okay, so the two factors is going to be charge and distance. Charge, we're going to use as Q's. This might be the positive ion, and this is going to be kind of like the negative ion. And there is also a constant in here, so I'm going to do kind of like this, just kind of say there's an approximation here. But as the charges increase, lattice energy will increase. And we see that from positive 1 to negative 1s, to positive 2s, negative 2s, to positive 3s and negative 3s. We can see this lattice energy really, really starting to increase. Okay? And as distance increases, the lattice energy goes down. So this is kind of Coulomb's law, okay, which talks about charges and distance. Okay, as the charges increase, the energy increases. As the distance increases, the energy actually goes down. Okay, so the strength of the lattice is going to depend on those two variables. Okay, the charges of the ions as well as how close we can get them to each other. And as the charges increases, the lattice energy increases, but as the distance increases, the lattice energy goes down. And I hope all this information was helpful. If this helped you understand why ionic bonding takes place, or help you understand what a lattice is, or the explanation of what lattice energy actually represents in an energy diagram, if this is helpful to you, please do a like and subscribe. That helps the algorithm get this information out to other students that are interested in learning chemistry in a straightforward fashion.